Okay. So we use an ability to take limits of functions where x is any real number to take the limits of only particular pieces of that function. And that's why when they draw some kind of picture, then they just select only points from it to show that if entire function approaches someplace, well, then those points that selected will also approach to it because that's a portion of that entire thing. And that's why they say if we have x, which is element of real numbers, then when n is a whole number, those limits are going to be the same. In other words, if we have the more general domain of a function, and so covering everything, and it goes someplace, we have a limit. Then here is going to be exact same thing. So technically, I don't distinguish between those variable like x or n, and I just going to use methods of calculus 1 to find this limit. So it looks like degree of the top is 1, and degree of the bottom is also 1 because it's squared, but square root is 1/2. So when I multiply by 1 over n, nothing is going to change. You can cancel it, but then you bring this 1 over n inside the square root so you can nicely distribute it, right? And that's how you find what the limit is. So it looks like 2 will be on the top because the n and n will cancel. And on the bottom, when you bring inside your square root that 1 over n squared, you end up with dividing n squared by that n squared that we brought inside and plus 1 divided by n squared. And the upper portion disappears, so we just have 1. And this piece is going to turn into 0 because our limit says that n goes to infinity. So we divide by big and we get small. And this ends up being number 2. No matter if you use n, just pieces, just those points, or x, which is anything real, the result is the same. So I guess the key idea of this section was to transfer our knowledge of the limits of functions onto the limit of so-called sequences that could be turned into functions, and that's exactly what they're doing here on the pictures, like part A or C. So you can see that we just care about those y coordinates, and we see that they seem to approach down to 0 or something in that region. So this is what we did in the beginning of this chapter. And now we're going to move on to slightly different story, but it is quite similar in a way. So now we're talking about series. So series are not really sequences. They're sums of terms of sequence. So you say, so you keep adding more and more numbers, piling them up on the top of each other, and you're talking about possible convergence. Isn't that going to be infinite if you add infinitely many numbers? And the answer is no. It's not the case if you just have something like 0 and 0 and 0 and 0. So definitely the sum is going to be 0, right? But there could be some non-zero numbers that will also have a finite sum. For instance, if you look at the following sequence, such as 1/2 And then if you add a half of it, which is going to be 1/4, and then you take a half of that remaining part, which is going to be 1/8. Do you see what's coming out? You're getting a half of what remains and adding it 1/16 and then 1/32. So if I add interesting set of fractions, such as 1/2 to the power that keeps on increasing, then the sum intuitively is going to look like number 1, like the whole segment, right? So if I add this, it looks like this is gonna give me number 1, which is quite amazing, right? So you add in the numbers that are not 0, and they not like positive and negative, they compensate each other. But the result ends up being just a finite number 1. And that's quite interesting. And they actually trying to come up with some theoretical ideas behind this by considering so-called partial sums idea. So what they say is, if you start to produce sums in a way that you add finitely many terms of the sequence. So the third is 3, the third sum is 3 terms, the fourth 4 terms, n's sum will contain n terms. So they say that the actual limit, so when you take the limit of this n's sum, when n approaches to infinity, you get the actual number, we call it as sum of the whole sequence. And if it's a finite, well, we say that there is a sum, like in the example I have here, the sum is finite, it is actually number 1. But it doesn't have to be finite, it may be infinite, or maybe something that we can't find. So we have a way to get the algebraic expression for that entire series. So we say from 1 to infinity, we can use the idea of the previous section. So we take a limit when n, like b, remember we had b that was going to infinity. Remember those improper integrals? And the sum was from 1 to b. So I can find this sum, the n's sum formula. And then if I take a limit, because I know how to take limits, I could see if it's finite or if it's infinite, or if it doesn't exist. So if it is finite, then we say that the whole integral is convergent. I guess a good idea is to take a look at some of the examples here, because that's like a general definition. And here's the example that I just tried to illustrate to you. The conversions of these partial sums. I just want to make this mess to go away. So they start to add these fractions with denominator 2 to some power, like 1/2, and then you add 1/2 with a quarter, so you get 3/4, and then you put 1/8 on the top of it, you get 7/8, and etc. So you can see that it looks like denominator will be 2 some power, right? 2 to the first, 2 squared, 2 cubed, and numerator is to the power of n minus 1, 1 less, right? Analogously to this. So once you found this and sum, you take its limit. And notice that if I want to take this limit, what I can do is the favorite, get the largest power, which is to the power of n. So I multiply by 1 over 2 to the power of n, so by reciprocal of that, and the top and the bottom. So nice and changes. So we cancel these guys, and when you distribute, you're going to end up with 1 on the top minus 1 over 2 to the power of n on the bottom. And when you're taking a limit of this stuff, then when n approaches to infinity, this 1 over 2 to the power is going away. That's what they actually expect you to do here. And that's how they say that the sum is 1. They don't really do these little steps, but I'm sure that you know how to do these steps. And we just proved that the sum is 1 instead of geometrically given an intuition that we get a half of what remains and another half and closer and closer and closer, and when it's a limit, then we're actually going to hit 1. But that's algebraic, because in the example that I gave you here, there is a nice intuition that seemed to be quite straightforward, but there'll be various examples where there'll be no intuition. And approach of taking the limit of the partial sums is pretty neat approach that will work, but not too often, turns out. In the part C of example, you see when sum is going to be infinite, because no matter what number you select, let's say billion, well, you take billion terms and you're going to exceed it. And no matter how large the number you take, the more terms than that number will give you the larger partial sum. So we say there's no bound, and that's why it's infinite. So we say that series is divergent in here. So they consider in a bunch of interesting examples that have their own specifics. So one needs to, well, just start to get used to them a little by little. But there they come up with one very interesting kind of series, which is called geometric series. I'd like to clean this mess real quickly, then share screen again. And here comes a very interesting formula for a series like one I already shown to you, sum of 1 over 2 to the power of n. We just noticed that the sum is 1, right? It was 1. Actually, when n starts at 1, let's start n with 1, not with 0. So if you start with 1/2 rather than with 1. Oh, it's not hard to change. You just put like that. 1/2, and then 1/4, and then 1/8, right? And etc. And it's actually infinite sum. And we found that this is equal to 1 already by intuition and by the limit of the partial sums. And it turns out that this is also called geometric series. So you can think of geometric series as if you take the first term 1/2 and multiplying it with a so-called ratio. And then the next term you produce when you have that same first term, but multiplied again by 1/2, or you can say by 1/2 squared, and then by 1/2 cubed. So people say it's a 1, or first term is like a, and then a times that ratio r, and then a times ratio r squared, dot, dot, dot. So that's what they are talking about here. So they have the sum of the series where they deal with this ratio R equal to 1/2. And the first term A is equal to also 1/2. So we got this kind of series in here. And they say that the sum is going to be something like that. I say, really, let me check this out. What is the A over 1 minus R? Well, it should be 1. So let's check this out. A is 1/2, right? So I put 1/2 on the top. And 1 minus R will be 1 minus 1/2. So they actually came up with a formula. How about that? And notice when I subtract 1.5, I get 1/2 on the bottom and 1/2 on the top, and this is indeed equal to number 1. How about that? In this particular example, I just used the formula, so I was able to find the same sum third way. So one can say, so how come this formula works? Well, we can actually utilize the idea of a previous example where we came up with, remember, the limit of the partial sums when n was approaching to infinity equal to the sum of the series. So that's what they call as S. So what would be the partial sum? Well, Sn I can write out as a 1 plus, actually not 1, A, the first term, right? Plus A times R plus etc. Turns out plus A times R to the power of 1 less, because they're n terms, and first term does not contain R, so it's like a 0 power of R, right? And what they do then is multiply by R both sides. If I multiply both sides of this by R, then I'm gonna get R times S1 is equal to R times A plus A times R squared, etc. A times R to the power of n. But before that, I will write this term, so I'll be able to subtract and cancel. So when you subtract both sides of this equation, the left side and the right side, notice that this term will cancel with that, and this term will cancel with that, and so forth. Everything inside will cancel with the inside stuff. So you're going to end up with R times Sn minus Sn is the same as the last term left, A times R to the power of n minus A. And when I do a little bit of algebra, R minus 1 is here, and factoring out A, you're going to get R to the power of n minus 1, right? Then you can see what the nth term sum is A times this R to the power of n minus 1 divided by R minus 1. So that's what they actually came up with here. So I'm going over the little proof here. And then now I need to take a limit and see what happens if n approaches to infinity. Well, then this turns into S. And when n approaches to infinity, R to the power of n should go to 0. So you're going to get minus A over R minus 1 or if you multiply the top and the bottom by -1, you're going to end up with this expression, as long as r to the power of n goes to infinity. And for that matter, r needs to be less than 1. And that's the key observation. So if the number is less than 1, if you multiply it by itself, you take a portion of it, and again by itself, another portion of it, another portion, another portion. So you keep getting smaller and smaller and smaller, and it goes to 0, so it disappears. Like, that's interesting to think about. So anyways, this formula works for so-called geometric series, for the series in a form where we get all our terms that produced by keep on multiplying the next term by that ratio r, and again, and so forth. So whenever we have such a series, you get to find the sum of it right away. So you can see example part A in here, how they get to use this nice little formula, which I think is pretty amazing. In fact, that's the only formula we have for series. Everything else you need to do somehow differently. But when you have geometric series, like we already saw, 1/2 to the power of n, and that's exactly what we know, converges to 1, right? Then the result, they ended up with something like 6. Well, because they start not at 1, but at 0. So there is extra something that is added, extra number 3 is added to it. But anyways, the point of story, to get that sum, you need to know the first term, which is 3 here, and the ratio, which is 1/2. And once you plug this in the formula for the ratio, you use 1/2, and for the first term you use 3, then you get the answer right away. The sum of this is exactly equal to 6. So it doesn't matter what A and what the ratio are, as long that ratio goes to 0. As long this ratio to the power of n goes to 0, or if it's less than 1, because if ratio is not less than 1, then the formula is not working. So here's another example of that same thing. So you can see that if you have geometric series, now in your denominator, your power of 10 will be 2, 4, 6, 8. So it is geometric. You just multiply by, looks like 100, right? By 100ths every term. So it is going to be geometric. And you just care about placing the first term in numerator. And the first term is what they have here, whatever it is. And the ratio 100ths, you put 1 minus 100ths in denominator. So you get yourself a sum. And this is it. And they actually noticed that when they add in these numbers, the first one is 0.08, right? The next is 0.0008. And the next 0.8 will have not 2, but 4 zeros in front. So that's how they get the 0.8, and then again 0.8, and then again 0.8, 0.8. So that decimal could be treated as 8/99, which is quite amazing, right? So there are various math examples that are amazing in the system of numbers that we're using. We're using system of base 10, right? Because there are other systems of base 3 or base 2. We say that in a processor, they use system of numbers of base 2, right? Either yes or no, if that's right, or nobody knows what it is. So they say quantum computers, so who knows what system they use there, right? But anyways, it's presumably if system is base 2, then it's different way to write numbers, only with zeros and ones, or with base 12, or like Mayan numbers, what base they have, 20 or 24. If it's quite complicated to write numbers with different bases. That's why base 10, that's what we're using, seem to be convenient. But anyways, for computers, it looks like base 2 is used, so it's different. So anyways, these are interesting things to look at, and why don't I just look at some of the exercises at the end of the section. So we're going to look at this geometric series today. In other words, infinite sums that are dealing with those terms that produce by multiplying the previous by the same fixed number. Geometric. I say they're algebraic. Well, algebraic, we're not going to touch. I don't think we are dealing with them because I think their sums are going to infinity anyways, because we keep adding the same numbers, so we just get infinity. And so we exceed just about any result as long as we have enough terms. So arithmetic, I'm sure you heard word arithmetic, they're not touching geometric. So anyways, they talking about this geometric series and exercise like number 9, and they say, can you find the sum of this? And I say, yes, of course I can say that sum is infinite, because if you have 7/6 raised to the power of n, then notice that your ratio is 7/6, which is greater than 1. So you take 7/6, that's the first one, 7/6 squared, that's the second one. Notice that second one will be 7/6 times another 7/6. It's bigger than 7/6. Then you get 7/6 cubed. So you basically take 7/6 times 7/6, which is already bigger because we multiplied by number more than 1, and then again by number more than 1, it's even bigger. So it looks like clearly these terms happen to exceed, if you take infinitely many of them, exceed just about any value, simply because the ratio is bigger than 1. The ratio needs to be smaller than 1. Then we get geometric series, and then they converge. Here we also have a geometric series, but it diverge because the sum approaches to infinity. So one needs to be careful with this. And let me try problem number 19 now with the, maybe I'll get a little room for that. So I don't have to fit it in that little piece. That's when you get mistakes, when you start to fit your work in some little tiny piece of paper and then probably miss something and get it wrong. So advice is always get enough room, always get plenty of paper or whatever board, and that way I don't think you ever go wrong with these exercises. So the problem number 19, it looks like our infinite series. Let me write a few terms first, so we better see what is going on. So 9/4 is going to be multiplied by various powers of 1/4. So in the case when n equals to 0, so I say a index 0, the term will be 9/4 multiplied by 1/4 to the power of 0, which is just a 9/4 because this is my 0 power, which is 1. Next term, A1, will be same 9/4, but now it's multiplied by 1/4 to the power of 1. So whatever it is, I wouldn't really care right now, but just to get an idea what we're producing here. The next term will be 1/4 square for A index 2. And now I get an idea of how my A, the first term, looks like, right? The first term, they call it as A. And the ratio R that I keep multiplying by, and this will be 1/4. And again, produce the next, again, I multiply by 1/4, and again by 1/4. So we got two main numbers, first term A, and the ratio called R. So I can go ahead and utilize the formula we already saw and I memorized. It's a sum which is A over 1 minus R. So this formula is good to have handy because whenever you have that geometric series, when you produce again from previous term, the next one by multiplying it with fixed ratio, then right away you end up with some type of a fractional answer. So it'd be 9/4 and 1 divided by, so this is going to be 3/4. When I divide by 3/4, I multiply by its reciprocal, which is 4/3, and looks like this is equal to 3. Again, I can use this formula because my ratio is 1/4. It's less than 1. The ratio must be less than 1. It may be negative. It's fine. Like here in exercise 21, the ratio is negative. So the series will alternate in signs, but as long as ratio in absolute value is going to be less than 1, and indeed it is 1/4, then I can use the formula and get the result. So first term looks like is 15/4, right? Without that ratio. And then the sum, I can use the formula above, just take my 15/4 and divide this by 1 minus 1/4, which is 3/4. So I'm going to flip 3/4 and write it as a 4/3. So multiplying 15/4 by 4/3, it looks like it's 5. When you say, Alex, you did it with ratio equal to 1/4, but what's going to happen if your ratio is actually negative 1/4? I wasn't careful. Well, we will produce something a little bit different, obviously. Let's see what we will produce. So that's minus 1/4. So this would be 5/4, right? So I'm going to flip it and get 4/5. And what I get instead of 5 is 3. And I guess it's not surprising because looks like our series will have sign alternating terms in 21. Just look at this. Let me clean that a little bit. So first term will be positive, but the second term will be negative. And then again, we get positive, and then we get negative, and then positive and negative, and etc. So it looks like we have 15/4. I'm still in the exercise 21. And A times R, the second term, will be 15 quarters times negative 1/4. It's like minus 15 over 4 squared. And then that next term, a times r squared, is now going to be positive 15 over 4 cubed, right? Because we're multiplying this negative by another negative. And then next term will be, again, negative 15 over r to the power of 4. So please notice that they cancel each other out, those terms. Because one adds a little bit and then the other subtracts. Again, we add and then we subtract. So series alternate in science. And no wonder that our sum is going to be a little less, because some of the terms will get canceled. So it's lower the sum. So various interesting ideas one can get from this type of exercises. So series are geometric, sometimes converge, sometimes do not. So some series definitely are not geometric. We're gonna talk about them next time. And I guess it may be a good idea for you to tell if series converge or diverge. How about this one for a quiz? Can you tell me what you think? Is in exercise 10, this is geometric series. Is it gonna be oh, they already say diverge. No, that's not interesting. Okay, so I just didn't see it. So verify that series diverge. So how can I give you something that actually is more interesting than that? What about similar to it? What about series that will be 5 multiplied by 12 over 11 to the power of n? Analogous to this, but they already say it's diverge. So can you tell me, is this one gonna converge or diverge? There's a little quiz for today. Again, what you care about is this ratio, right? And it has to be going under big condition. It has to be less than 1. So the quiz question, converge or diverge? This is geometric series. So you have to write converge or diverge. And I guess that's all we need for today. That'd be good enough to start.